This is the 11th lecture on the lecture series on continuity, but I have purposefully kept the same opening slide from the last video saying that it is the 10th lecture. Actually, today's lesson should have been done before Bolzan's theorem, which we discussed in the last video. After establishing some of the beautiful properties exhibited by a continuous function on a compact domain, one should move to Bolzan's theorem, which immediately leads to intermediate value theorem, which in turn, taking advantage of the knowledge of the bounds of a continuous function on a compact domain, gives a better description of range of a continuous function on a closed and bounded interval. So please excuse me for this mix-up. The proper chronology of these videos will be: first, bounds on a compact domain, which we are going to do today; second, Bolzan's theorem, which we did in the last class; and third, intermediate value theorem, which we will be doing in the next class. With this understanding, let us proceed to today's lesson, bounds of a continuous function on a compact domain. So our first theorem today is a continuous function defined over a compact domain is bounded. Now, this theorem is not only true in real analysis. Any real valued continuous function defined over a compact domain in any metric space or even any topological space will be bounded. Let's see the proof. Let K be a compact subset of R and F defined over that compact set is continuous. Let X be any arbitrary point in K. Fix epsilon positive. Now, since F is continuous at X, there will exist a positive number delta, which will definitely depend on X, such that for any point X dashed from that delta X neighborhood of X, intersection K of course, the distance of Fx from Fx dashed will be smaller than epsilon. Now, if you break this up, you will get Fx minus epsilon is smaller than Fx dashed is smaller than Fx plus epsilon. This implies F is bounded on the delta X neighborhood of X intersection K. Now, since X is arbitrary, for every point X in K, we would obtain an open interval Ix, which is of the form X minus delta X to X plus delta X, that is in delta X at X, such that F is bounded on Ix intersection K. Consider this set of all open intervals Ix thus found and call that collection G. Then G is definitely an open cover of K. Now, since K is compact, G will admit a finite subcover, let's say Ix1, Ix2 up to Ixn. That is, K will be contained in the union of all these Ixks. K is running from 1 to n. Now, since for every K from 1 to n, F is bounded on Ik, this is Ixk, this must be, F is bounded on Ixk intersection K, therefore there exists an Mk positive number which will act as a bound of F in that kth interval around Xk. So there will exist an Mk positive such that for all point X in Ixk intersection K, the modulus of Fx will be smaller than or equal to Mk. Call M to the maximum of all these bounds in these K intervals. Then Fx will be, the mod value of Fx will be smaller than or equal to capital M, and that will hold for every point X in each of the neighborhoods Ixks. So union of Ixks, K is running from 1 to n, and definitely intersection K is hanging there with every one of them. But this is equal to K. K is contained in this union by this hypothesis. So this means F is bounded on K. And this completes the proof. The corollary is when you take the compact domain to be a closed and bounded interval. Now, definitely this does not require any separate proof, but for the sake of importance of this one, we are giving a alternate proof. This proof is valid wherever sequential compactness would be equivalent to compactness, that is in a metric space in general. If possible, let F be unbounded on AB. Then for each natural number n, there will exist a point xn in the domain AB such that mod of f of xn is greater than n. This is the definition of unboundedness. Given any number, f will exceed that number. So if you choose any number to any natural number, you will get a point where the functional value will be bigger than that number, at least in absolute value. Consider this sequence of points xn. Now, since this sequence is coming from the closed and bounded interval AB, it is bounded, of course. Therefore, by Bolzano-Verstra's theorem, Xn has a convergent subsequence Xnk. Let's say converging to a point, say xi. Since AB is closed, xi will belong to AB. Consequently, f is continuous at xi. Therefore, by sequential criteria of continuity, f of xnk, that subsequence, will be a convergent sequence and hence it will be bounded. But by our construction, mod of f of xnk is greater than nk, and which is definitely greater than or equal to k by the definition of subsequence itself. That is, f of xnk is an unbounded sequence. F of xnk, mod value of f of xnk is greater than or equal to k suggests that f of xnk has to be an unbounded sequence. But that is a contradiction because it is a convergent sequence and at the same time it is unbounded. So that is a contradiction. Hence, f must be bounded in it. That our assumption that f is unbounded of AB is not tenable, and f therefore has to be bounded on the closed and bounded interval AB. Now, this proof is very much valid in a metric space where we can talk about sequences, but this is not valid in a topological space. Remark: a continuous function defined over a non-compact domain may be unbounded. For example, the function x going to 1 over x is coming from open interval 0, 1, which is not a compact set, is continuous function but unbounded on 0 to 1. As it tends to 0, it gets bigger and bigger. The second remark: let K be a compact subset of R and let F be a continuous function defined on K. Since f of K, which is the range of f on K, is a bounded set by the earlier theorem, both the bounds, the supremum of fx over K and the infimum of fx over K, exist finitely. In this line, our next theorem says a continuous function defined over a compact domain attains its bounds. This theorem has a major application in the optimization problems. A continuous function attains its bounds. You have points in your domain where the function becomes the supremum in its range and another point where the function becomes minimum, infimum at this range. So your supremum and infimum in the ranges become maximum and minimum of the function. Proof: let K be compact and F be a continuous on K as usual. Call capital M as the supremum of F over K. Then for every natural number n, you get a point xn in K such that m minus 1 over n is smaller than f of xn is smaller than or equal to m. And this we get by the definition of supremum of a set. Because supremum is the least upper bound, and if we make that any smaller, any lesser, then it will not be an upper bound anymore. So it will be exceeded by some point from the set. So the points on the set are the f images of the points x, and therefore it will be exceeded by f image of a certain point. So m minus 1 over n will be smaller than f of xn for some point xn coming from the compact set K. Now consider the sequence xn from K. Since K is compact, it is closed and bounded. Consequently, the sequence xn is also bounded, and therefore, by Bolzano-Virchow theorem again, admits the convergence of sequence xn K, converging to a point xi, say. Also, as K is closed, xi belongs to K as usual. Consequently, f is continuous at xi. By sequential criteria again, fx and k converges to f xi. The sequence fx and k converges to f xi. But by construction, for every natural number k, m minus 1 over nk is smaller than f of x and k is smaller than or equal to n. Now, nk is a strictly increasing sequence. So 1 over nk goes to 0. Therefore, the left hand side tends to m itself, and therefore by sandwich theorem, the sequence f of x and k tends to m as well. But f of x and k converges to f xi, so therefore f xi has to be equal to m. Similarly, we can prove the existence of a point eta in K such that f of eta is equals to infimum of fx, where x is padding over K. This also has an alternate proof called m as the supremum and assume that m is never attained by f. Therefore, for every point x in K, fx will be strictly smaller than m. That is, m minus fx will be greater than 0, and this will hold for every point x in K. Now define a function phi over the same domain K by phi x is equal to 1 over m capital M minus fx. Definitely, phi is continuous on K. Now, since K is compact by the earlier theorem, phi is bounded on K. Let the positive number capital B be an upper bound of phi on K. Then, for every point x in K, phi x is strictly smaller than B, but this implies 1 over m minus fx is smaller than B. That is the definition of phi. But this implies that fx is smaller than m minus 1 over B. This contradicts to the fact that m is the supremum. So here we see m minus 1 over capital B, where B is a positive number, is a smaller quantity, is a strictly smaller quantity than m, and we are having every point of this set is smaller than m minus 1 over capital B. So capital M cannot be the least upper bound. M minus 1 over capital B is smaller than capital M and is performing as an upper bound. So capital M cannot be the least upper bound. That is a contradiction. Hence, M must be attained by f, so that we can never define this function phi x is equal to 1 over m minus fx. Similarly, we can prove that infimum of f over k is also attained by f at some point in k. Remark: a continuous function defined over a non-compact domain, even if bounded, may not attain its bounds. For example, the function fx equals to x on the open interval 0, 1 is bounded. The infimum and supremum of f on 0, 1 are 0 and 1 respectively, of course, which are never attained by f.